In this demo, we are going to be modeling a free surface system. A free surface simulation is used to study sloshing, vortexing, and changes in fluid level due to injections and/or draining. The approach uses a volume of fluid, or VOF approach. Free surface simulations are compatible with all other features present in MSTAR CFD, including moving geometries, reacting scalars, particles, and complex rheology. Starting in MSTAR Pre, we will first add a primitive tank. We can rename the static body parent Tank and rename the first child Walls. We'll make the bottom of the tank flat, remove the baffles, and make the diameter and height 0.5 meters. We'll add another child to the tank family. We're going to rename it the dip tube. We're going to make this a primitive cylinder geometry with a diameter of 0.02 meters and a length of 0.3 meters. Using the translate option and then the snap functionality, we can move this cylinder directly to the top of the tank. We're also going to offset this 0.1 meters off the tank center line. We'll then add a moving body and choose pitch blade impeller. We can rename this parent to PBT. We'll set the rotation speed to 330 RPM. We'll set the impeller diameter to 0.2 meters and set the shaft length to 0.35 meters. Now we'll offset the impeller 0.15 meters off the bottom of the tank. This model, by default, is a single-phase simulation. We're going to change this to a free surface simulation by clicking on Create and then going to Free Surface Simulation. Here, we'll change this to shaded to make things more clear. The blue box describes the initial fluid height within the green simulation domain. As with the single fluid simulations, the green bounding box defines the extent of the simulation domain. The blue box within the simulation domain defines the initial location of the liquid within the simulation. Note that the domain can be initially empty should we seek to model the filling of an initially empty system. In this case, however, we will set the initial fluid level to 0.35 meters, which corresponds to about 50 liters. If we want to specify an initial fluid volume, we can select the volume calculator and specify a fluid volume. The code will then use an iterative approach to identify the fluid level that corresponds to this user-set fluid volume. This feature is particularly useful for tanks with complex topologies, wherein the link of the fluid level to the fluid volume is not immediately obvious. Note that the displacive effects of the impellers on fluid volume can be included in the volume calculation. Here we will set the fluid volume to 50 liters and choose to update the fluid level automatically. The modeled fluid is water with an LES turbulence closure model. The free surface model uses a volume of fluid approach. As such, although the pressure and gas in the headspace can be specified and controlled, fluid motion in the headspace is not captured explicitly. We can adjust the rheology and density as desired to include non-Newtonian fluids or fluids with custom user-defined viscosities. To help visualize the flow, we will add tracer particles to the simulation. Tracer particles are non-inertial, non-interacting point objects that evolve according to the local and instantaneous fluid velocity. They are useful for visualizing flow fields and characterizing blending. For open systems, they can be useful for characterizing residence time distribution. We will inject particles into this small cylinder near the tank wall. We will dump 100,000 tracer particles at 5 seconds. And we'll set the simulation resolution to 200, which is sufficient to predict power draw for this impeller and flow around the dip tube. We will use the default Courant number and set the runtime to 30 seconds. In the output control, we will choose to output the free surface velocity. This will print the velocity at the interface. Now we'll run the simulation. We want to keep our eye on the LB density to make sure that both the minimum and maximum values stay within a few percent of 1.0. This value quantifies the appropriateness of the simulation time step. If the LB density variations are too large, the solution is not a valid solution of the incompressible Navier-Stokes equations. In such case, the Courant number should be decreased to lower the resulting LB density variations. If the LB density is within a few percent of 1.0, the time step is sufficient and the solution is converged. If we open MSTAR Post, we can see the simulation running in its first few time steps. Here we can see the position of the interface, as well as the fluid moving along the output planes. If we change the color scale on the planes from 0 to 2 meters per second, we can let the code run and see the fluid move. After the code is run to completion, we can refresh all the data, we can turn off the planes, and render the free surface by velocity going from 0 to 0.5 meters per second. We'll make the time text a little bigger as well. The system is showing significant vortexing such that the free surface is interacting directly with the impeller. The dip tube is having no material baffling effect on the flow. We're going to turn on the particles and change the color to red to make them easier to see. Since the particles are tracer particles in this simulation, the particle diameter is only relevant for visualization purposes. Again, in other tutorial videos, we will discuss modeling internal particles, two-way fluid particle coupling, and CFD-DEM simulations. Here at 5 seconds is when the particles are injected into the simulation. As we advance through individual frames, we see that the particles are following the strong azimuthal flow motion inside the vessel. After about 3 seconds, the particles are well dispersed, but the dispersion of the particles was governed by the swirling motion of the fluid. We're going to make the view orthogonal here, adjust the particle diameter for rendering clarity, and save the animation. We're going to export the video at 10 frames per second, printing the visualization data every 0.1 seconds. This makes the animation a real-time representation of the flow field. We will now extend the system to include filling and volume changes. If we go back to MSTAR-Pre, we are now going to add fluid to the system through this dip tube here. We will go to Create, Add Inlet, and then select the edge at the bottom of the pipe. We hit the flip direction to change the surface normal. This surface normal vector informs the direction of the flow at the inlet. We'll rename the inlet Dip Tube Inlet. Set the boundary condition type to Inlet Single Pulse. Set the pulse type to Volume Flow Rate. We'll set the volumetric flow rate to 1 liter per minute and the start time to 1 second, and we'll set the duration to 15 seconds. With this specification, after 1 second of simulated time, fluid will enter the system through the dip tube with a volume flow rate of 1 liter per minute. After 16 seconds of simulated time, the flow will stop. Because the free surface is active, the total fluid volume will increase by 15 liters as a result of this fluid addition. The position of the free surface will change as a result of this fluid addition. Note that flow rates can be negative, implying fluid leaves through the outlet. Also note that the flow rate can be arbitrary user-defined functions. We will keep all of the simulation parameters the same, and we will rerun the simulation. If we open up MSTAR Post again, we can observe this simulation. We will hide the particles for clarity. And as we play back the video, we can see the fluid level rising slowly. The vortex is persistent through the filling process. We're going to plot the data of this simulation and take a look at the graphs. Beginning at 1 second, the fluid volume level increased until 16 seconds. The increase in fluid volume between the ends of this filling interval was 15 liters. Looking at the LB density, there were some fluctuations that approached 8%. Although these results are acceptable, we might recommend rerunning at a Courant number 25% smaller to present better control on the time step. We're going to save this movie as well, at 10 frames per second. And as we play back the movie, we can see that the volume change due to the added fluid is obvious, although this addition has no change on the surface vortex. Likewise, the dip tube presents no material baffling effect on the flow even at this elevated fill level. Thank you for watching this tutorial video on free surface and filling simulations. Please reach out with any technical or application questions.